conceptual questions. I think we went through these in a lot of detail, so I'm not going to really say anything about those. I think the key thing with this is recognizing that you're going to end up getting a current that's in a direction to cause a temporary magnetic field to oppose the change in flux. That's a mouthful, but the idea is, for example, here, if this wire is going down, we're increasing the magnetic field that's coming out of the board. So therefore, to oppose that, we would want a current going that would cause X's inside of this area, meaning a magnetic field into the board, and again, that would be a clockwise current. So down here, I think we discussed all these. This one was a complicated one. And again, I think this one not too bad. So the idea here is that, again, if the magnetic field's increasing in strength, you would want to oppose that by making the area smaller. If it's decreasing in strength, you would want to make the area bigger. So you're going to get an induced field to cause a force either acting to the left or to the right. So going to the problems. So in this particular case then, number 2, nobody asked about. That should be just a simple BLV. Here, you're going to look at the current is going to be E over R. So the voltage you would use BLV to get, and then the current, therefore, you get 1.13 amps. That would be a clockwise current because the clockwise current would end up opposing the change in flux as it exists, which is decrease. So essentially, again, we're going to have a clockwise current which causes the magnetic field strength inside here to increase. So for 4B, when you're asked to figure out the force of this, there's a couple ways you could do that. I did force times velocity here, but you could also do B times I times L. So you could do the 1.4 Tesla times the current, which we got is 1.13 amps, times that length of the wire, which is 0.05 meters. That would also give you the same force. For problem 10, essentially the net field here in terms of the Webers, if we look at it, the area here, 0.04 meters times 2 Tesla is in, 0.04 meters times 1 Tesla out. So we end up having a net flux into the page of 0.04 Webers, 0.04 Tesla meter squared. For problem 15, the key thing here is you had 1,000 turns, so it would be 1,000 times the strength as opposed to when you figure it out using the change in flux with respect to time. This one is the one we went over in class. For number 20, ended up having a radius, or pardon me, a resistance of 0.1 ohms. So it told us that it was a 0.15 amp counterclockwise current. So that meant that we would end up needing 0.015 volts. Well, that's going to equal the change in flux with respect to time. We know the area, so we can find change in flux with respect to time times area would equal that voltage. And that gives us, I believe, 2.34 Tesla per second. Sorry, kind of screwed up how it looked over there. For number 21, we did this one in class. So I almost screwed up because I was only looking at the 2 volts of EMF causing the current, but there's already a 9-volt battery. So based on how the field was changing, this would cause a clockwise current. So that basically means that the voltage is in the same direction as this 9-volt power source. So that equals 11 volts. 11 volts divided by 20 ohms is 0.55 amps. If we had it where the voltage was going to cause a current counterclockwise, which would be if this field strength was decreasing, then it would oppose the 9 volts, and that would be a net of 7 volts, 9 minus 2. And that would be somewhere like 0.35 amps. This one is very similar, number 65, to some of the things you've got in active physics. So we've got a 2 ohm resistor is being pushed, so it's going 0.5 meters per second. You know the cross-sectional area or length of the wire is 0.1 meters, so we can use BLV to figure out that voltage. You could also use change in flux with respect to time, which is B delta A over delta T. So I get 0.0125 amps. Here, BIL, that's the force on the wire, and that's the force that you would need to basically keep this thing moving, because there's going to be a force backwards. So that's 0.0000625 newtons, or 6.25 times 10 to the negative fourth newtons. I did this a little differently, so I could have done an F times V. So that force times that velocity will give me 3.125 times 10 to the negative fourth watts. Or I could have done P equals I squared R, give me the same thing. And then this current's going to be counterclockwise to oppose the change in flux. I'd already figured that out above. And this power that's dissipated is the one where you'd use I squared R. You could also use F times V. I think that's it.